Hello, good morning, everyone. How are you all? Um, so, let me open everything up. I think some of you are out there. Good morning, Robin. Hi, Isla. Hello, Alex. Okay, good morning. We're here. Hi, Luis and Sanjita and Nathan. Good morning. Um, so, welcome all to Monday. We have our exam today, followed by a lecture. So in I'm probably just going to talk for like a minute or two, and then I'll update our campus so that you could see the exam. Um, and the first thing I want to say is during all these exams, you're going to possibly run into any sort of technical issues, and we can resolve any of those issues, you know, in the exam, during the exam. Good morning, John. We can resolve any of that, you and I. I will have my chat window open the entire time, so you can send a private chat to me and we can figure it out. If it's a question about the exam, also feel free to use the private chat and we can figure out or clarify any question you might have. Um, if we're if you're talking to me through the private chat or you've sent a question and I'm taking a while to respond, just know that I'm going through the line of people asking questions and I will get to you. Just kind of hold tight. Let me see. I think that might be it. I will give you some timing, right? I'll tell you when there's about 30 minutes left and about 15 minutes left, and then 10 minutes when you should start submitting. Um, the next thing is don't leave anything blank on the exam. Do your best to write down something. If it's blank, that's a definite zero. If there's something, you can get partial points, right? So make sure you write something down. Um, yeah. Okay. So the last thing is, take a deep breath. Do not freak out over anything that happens. Good morning. And, uh, you know, anything that happens on the exam, you can certainly fix throughout the class. So this exam is not going to make or break your grade. So kind of just, take a deep breath and take a moment there. And good morning, everyone else, Gary, Daniela, and Andrea. Um, okay, I think I am ready to upload the exam. Are we ready to go? Okay. Everyone take a deep breath, okay? You're going to be okay. I promise you, you'll be okay. We just got to get through the first one. You are going to be ready. Okay, let me update then the timing on it. It's 03, and you will have a full hour to finish and submit the exam. And so you're going to see
Which
that. Uh-huh.
which category is like the exam found under?
You're going to see it under module 1 at the very top.
Oh, okay.
Yeah. Okay, let me, one more announcement. So you'll have about an hour, which means about 11:05-ish, right? Um, we will take a break until 11:30 and come back for lecture at 11:30. I'll put that in the chat too. So come back for lecture after 11:30. Once you finish the exam and submitted it, you're free to do anything you'd like. Good morning. Yeah, once you finish the exam, submitted, you don't need to tell me anything. You could just go do your thing. Okay, so I'm changing everything for 11:05 right now, as expected. No, you do not need to have your camera on. Um, I don't know. You don't need to have your camera on. Okay, so let me just update it to 11:04. Okay, if you could all refresh your Canvas page and see that you see the assignment and the PDF file. Um, if you see it, just go for it. Okay, 1 hour on the clock. Let me put a timer on and I'll be here. I'm gonna mute myself and everyone. Feel free to send me a private chat. You can submit the answers any way you want, Destiny. There's no writing the questions, all that's up to you. All I care about are answers. Hi, everyone. I just want to remind you that you have a little bit over 30 minutes left, so keep working on the exam and get ready to submit in about 20 minutes or so. Also, I was told about a typo on number 5. It's just a matter of words. It won't affect the physics of the problem at all. But when you see the word drone, it really means the car. That's it.
You said the drone and the car are the same thing? Okay.
Hi everyone. You have about 15 minutes left total. So I recommend you work for about 5 more minutes and start submitting after that. But 15 minutes left total to submit. Hi everyone, the exam is due in exactly 10 minutes. I recommend that you wrap up anything you're solving and start submitting. The exam is due exactly at 11:05 a.m.
Oh, Professor. Professor, I have a problem. When I convert it to PDF, the file doesn't wanna open with me. How I can do this?
Nada, I'll let you figure that out. You have enough time to submit. If you'd like to email it to me, you can, but everything else, please send it to me through chat.
Okay.
Hi, everyone. You have about 5 minutes left to finish the submission. If you're having any issues, you can always email me as a backup, but as a backup only. Continue to create your PDF and submit. And I'll see everyone at 11:30. Your exam is due in 5 minutes.
Will we go over the exam or anything today or no?
Hi everyone. So it is now, the time, the due time for the exam. So if everyone's pretty much submitted, but if you haven't submitted yet and you're still working on it, continue to do so. The link is still open. It will be marked late, but continue to submit the PDF. For everyone else, we were going to have a lecture starting at 11:30 and it will end at 12:30. So come back for 1 hour at 11:30, and we'll start chapter 4. And enjoy your break. I'm going to take a few minutes to catch up with the chat, and I'll see you all at 11:30 on the dot.
See you then.
See you.
باي باي.
Hi everyone, welcome back. Let me get my light here too. How are we doing? um, I hope y'all are good. Let me see. I'm gonna open my chat really quick. Okay.
Hey,
Hi. So let me start by telling you what the next hour will look like, and then we'll see, what kind of what else we can add in. Everyone is still on private mode in the chat, so if you want to switch it over to everyone, that's cool. Or if not, that's cool too. Um, so I think I'm okay with spending about 10 minutes to see how you're all feeling about the exam.
it was
But
brutal.
hold on. But I will ask that you don't talk about the problems, because there are still some people out there that are either working on the exam or did not submit the exam, something. So I prefer if we didn't talk about the problems for 10 minutes. Now, after class, if you'd like to stay and ask some specific questions, I'm totally okay with that. I will stop recording and we can talk about it. I have no problem with that. Yeah, so 10 minutes, how are y'all doing? Any feelings about the exam?
I feel brutalized.
Oh, I'm sorry you feel that way, Randy. It'll get better, right? And I see a lot of other thumbs up. Um, Isla said I kept overthinking my sig figs. Hi, Mehmet, how are you? Hello, Keon, too. I see also the thumbs up. Others said pretty good. I thought it was good. Very good. Very nice test. Yeah, I did get several submissions around maybe 10:45 or so, which tells me that you guys were working right on it, which I'm very excited about. I see a medium response also, which is good too. And we also have the other spectrum, a brutal, or a Jay said it could be worse. Yeah, and the point of the exam one is just to figure it out, right? See what works for us, see what adjustments we can make next time too. Yeah, yeah. Any general comments?
So I thought the sig fig problems were pretty simple. I thought, and then the physics problems seemed like more challenging, because you have to figure out which variables like go into which equations and such, but it
Yeah,
wasn't that bad, I don't think. So
yeah. Thanks, Nathaniel. That's a good comment, and I really like the word that you use, challenge, because I didn't want to say this before the exam to freak you guys out even more, or but the exam shouldn't be easy plug and chug. Sometimes you might feel a challenge, and you have to get comfortable with the uncomfortable. That's the only way we grow and get better at things. Yeah. So, and Daniela said the drone error also almost got me. Yeah, I didn't even, I go through these exams so many times, checking them over and over and over and over, and I still have typos, right? So that was a typo. I didn't mean to throw you guys off with that. And I was going back and forth in my head between, a drone, an autonomous car. So yeah, I'm glad someone pointed that out to me. Oh, the equation sheet definitely helped. Good. And I hope what you guys see is how you can adjust your equation sheet to help you in the future too. And then someone says to me, the material was similar to what we covered in class, so we had no excuse. Yeah. Yes, but I will say that we all kind of take things differently. And the comment says, my adjustment would be to study more of the homework, but nothing that if you don't put in the time, you won't understand. Yeah. Um, yeah. And yeah, I appreciate that comment too. But again, if you felt the exam was challenging and hard, that's okay. There's, you can just keep working on it little by little. Being aware of what you find challenging is so important. So once you recognize that, we make adjustments. Will other exams differ more from problems reviewed in class in terms of difficulty and or extensiveness? Um, there will be some difficult problems, but the difficulty should never be time consuming. The difficulty only comes if you forget something. I'm going to throw this out there, and I'm hoping not to start a riot in the class. for example, an acceleration can be constant. It can be a number.
Yeah. So that's where things like tricked me. Like I felt like a lot of it was too simple, and then I overthought, and I was like, "There's no way this can be right. There's no way it can be right."
That's another one. I'm so happy you said that, Randy, because I knew someone was gonna say, or message me and say, "This seems too easy. Am I wrong?" And
Yeah.
guys, it's okay to think something is easy if you put in the work and the two relate. If it's too easy and you didn't study, perhaps you might you might think about it. But if you studied the homework problems, you studied the lecture problems, and you think it's easy, it's because the material is familiar to you. And I hope it's okay. It's okay to think that. Yeah, so just to be very clear on Gary's question, in terms of difficulty, nothing will ever be time consuming where you can't complete a question in about 15 minutes or less. Same with extensiveness. I'll say quickly, the only thing with a lengthy problem is if there is a lengthy problem, I will balance it with a short problem, which is what I hope you saw in the first page of the exam.
I do have like a slightly specific question that kind of threw me off.
Is it about a problem or a general topic?
It's kind of about a problem, but it's just about a note on a problem like that you put in. You say like reminder, make sure to use vector notation. And then I'm not sure if it was a dash or a negative. So I thought it read reminder, make sure to use vector notation. Negative vectors are special.
Oh no.
Or does that just mean vectors are special?
It was a dash. It just meant vectors are special.
Oh, okay.
I'm just reminding you when I say vectors are special, put the arrows and the hats. That's all I'm reminding you about without
okay.
saying it. Yeah. Okay, and the last comment I'll take. It wasn't that hard, but you have to analyze it very well. Usually my problem is the time because I feel I don't have enough time to analyze it well, but I think it was okay. Okay, I'm glad you felt that time was okay. Usually when I start this exam, everyone says there's not enough time. And believe me, time is not the solution. Time, it's more about, like you said, Andrea, analyzing it. And if you're to a point where you're analyzing it and nothing is coming to you, or you're just stuck, you probably aren't prepared to answer the question. And you just got to do what you can for the test at that point and move forward. Yeah. Okay. After class, yeah, I hope exam 2 will be better for everyone, a better experience too. After class, I'm happy to stay, especially because today we're only gonna go until 12:30, no matter where we are. And then, hello, Kitty. And then I can stay and I will stop recording and we can discuss any comments that anyone has specifically. But I will also say, also be comfortable with not having an immediate answer. Instant gratification is not always good for you either. I'd rather you take some time and think and then come back to me, but I will stay for whatever you guys want to talk about. Okay, let me start my slideshow and take us into some physics. Is the cat sharing your food, Keon? Oh, I left my water.
Yeah, the cat likes to lick my oatmeal bowl.
Oh, the leftover. Okay. Or like the little bit. That's funny. Oh, so cute. Sounds like your dog too, Owen. Okay, I left my water. I'm just gonna grab it really quickly. I'll be right back. 2 seconds, maybe 4.
Oh, your blanket fell.
Okay.
Oh, there's a cat.
Oh, we see the cat. How cute. Okay.
Your blanket fell on the ground. Your blanket fell on the ground?
My blanket? Oh, it's okay. I only have it for sometimes when the backgrounds weren't matching, I'd put a different color. Just, yeah, not for like coldness. I gotta get rid of this chair too. I found this chair in the freight elevator in my apartment. But then, yeah, anyways, long story. Yeah, I should get a much better chair. I agree with you guys, totally. Yeah, I've been looking, but I don't know. you. It's a lot. Okay, let me shift my screens around. I hope you guys can see my PowerPoint on the big screen. And then I'm gonna move your boxes around. And I see the chat. Yes, so I agree with with Saja about the chairs. I do believe that they're expensive. I do think they're an investment though, so I do agree with that. But I don't know, more to think about. Yes, I would. So is back surgery. That's right. So I do agree it's an investment. Yeah, I have other things that help my chair out. Yeah. Okay, so let's get ourselves back into the world of physics, and we're gonna get into like some real physics now for chapters 4 and 5. I don't think we'll get into chapter 6, but chapter 6 is covered a little bit in chapter 5 and a little bit in I think week 4. So you won't miss the content, you just won't get it in the order of in chapter 6. That's all. But we are going to go into a 2-dimensional world now. So everything we've done so far is in 1 dimension, either along the horizontal or along the vertical. And now we can see that we could, using our vector math that we learned in chapter 3, we could write everything in terms of 2 dimensions by pulling that vector math into our physical world. So here you see an example of this person who's trying to make it to the library, and we know the straight path is the shortest, of course, but if you're in, a city, you can't always go diagonally across a block. So we could write this in terms of movement or displacement in the x and displacement in the y, and now we can get what is the position vector in terms of this exact location here. So I'll just say this is my 0, right? This is my 0, and I'll take every block as a unit. This point right here where the library is located could be written as, this is the r displacement vector or the position. And this can be written as, let's see, 1, 2, 3 in the negative. So I would write -3 I hat. And then 1, 2, 3 in the positive, so +3 j hat. And if I gave a physics student this equation, you could get to that library position, right? We broke down this position x in terms of its x dimension and y dimension, horizontal and vertical. So this is nice along a grid, right? But you'll see in physics and in everyday life that the straight line motion, it doesn't always describe what we see. So for example, you'll see someone welding, you'll see sparks flying, right? Or if you go to a water fountain, maybe next year, if you go to a water fountain, you'll see the movement of the water coming out like this, or someone jumping off of a cliff, or even the fountains of the water fountains with water shooting out. You see different motions, but not a straight line. Anyone see any similarity between all of this motion here?
Parabolas.
Yeah, I heard the word curves and I heard the word parabolas. Owen is saying it's parabolic. That's correct. You'll see that projectile motion, no matter where it leaves, will always come back down if nothing is acting on it. Notice that nothing is acting on it here. Nothing is acting on this person here. Nothing is acting on it. And Bafar says it's projectile. Yeah. So this would be what we would describe as projectile motion. But what is making this kid come back down and this water come down and this
Gravity?
Yeah, it's all gravity, right? Gravity is a physical quantity that exists. Okay, I won't say a physical quantity. It's a quantity that affects physical objects. It's a I'll call it a force for now, a gravitational force, we'll say, that exists, that is going to act on objects. And notice that gravity here is always acting downwards. It's always pulling everything back down. We push the water out of this fountain and this fountain out with some force, and then if nothing else acts on it, gravity that exists will always be there. Yeah, so if something is shooting up, like Bafar says in the chat, and if nothing physically is acting on it, gravity will act on it and it will come down. If you want to shoot a rocket into space, you have to overcome that force of gravity, right? To shoot your way out. So our goal then is to describe everything that we did in chapter 2, position, velocity, acceleration, and to now describe it in 2 dimensions, right? How can we do that in 2 dimensions? Well, we can use all of the vector math that we just did in chapter 3 and I'll remind you that a vector will denote a magnitude and a direction, always. It denotes both of these. So magnitude and direction, right? And we know now that our position is a vector, right? Our position R is a vector, our velocity is a vector, and our acceleration is a vector, right? So all of these have something to do with magnitude and direction. If one of these stays constant but the other changes, there is still a change in general. So let's look at what these position vectors look like then. So our first position vector now, we will take our same equation from chapter 2 where we described the displacement as x final minus x initial, but we're now going to describe it with r, the position vector r. So this is similar to what we saw in chapter 2 when it was all in 1 dimension. And now we're writing it in 2 dimensions, and notice that there's a bold-faced vector with an arrow on top, and each one of these vectors represents its own vector, and if we subtract them, we can take that position or displacement vector. Now, our goal isn't to be able to do this graphically. We want to do this mathematically, right? We want to do this analytically with our vector rules that we have from chapter 3. But all you want to really recognize is that we're no longer going to work with just kind of one vector that you see here, but we're going to describe that second position, point B, also with a vector, and we can describe and we can subtract the 2. So notice that point A has an x and a y coordinate, and point B has an x and a y coordinate, right? So we can describe both of those with this position vector. Now, when we're looking at this position displacement vector, they're the same thing here. We know that if we look at it over time, we can also get the velocity vector. And then if we look at the velocity vector over time, we can also get the acceleration vector. So we could write those down also. So that's a V. I know it looks funny, but that's a V. The velocity vector here will be the derivative of the displacement vector over time. And we can write the same way, right? We can write the same way. Acceleration vector is equal to dv over dt. And I see a question. Is it orbital mechanics that teaches us the changing gravitational force as we move away from the surface of the Earth? No, I don't know if that's orbital mechanics, but the definition of a gravitational force will be proportional to the distance. So that's just the definition. And you'll see that in this class the last week when we move from the value of G, and we'll start talking about what is the actual gravitational force. And you'll see some constant here, capital G, mass 1, mass 2 over r squared. And what you're referring to is the relationship between the force and the distance here. But you'll see that in the last chapter. But yeah, I'm glad you're pointing it out, because that's some fundamental physics you wanna start catching on. That the observation is that the further away you move, the less force the object has on you. That's really good to point out. Okay, so now
So are you saying that with that the vector v is equal to the derivative of the position over time?
Yeah, that what you just said is what is written right here. And this is a V. That's a V. Yeah. Yes, the force of gravity is the inverse of the radius squared. That's the exact relationship you want to be able, and saying that over and over, I hope eventually has some actual physical meaning versus just the mathematical meaning that you see here. Those relationships are so important. And so we see the relationships here from position vector over time, that's velocity, and velocity vector over time is the acceleration. So each one of these can now be written in terms of their vector notation with the derivative, the actual mathematical relationship that we know, right? So what I want you to take from this is that the displacement, the velocity, and the acceleration are each vectors. They can be written in terms of their magnitude and direction. And we're looking at them, how each one of them moves over time will give us some value of some sort. So before we start writing them out explicitly in 2 dimensions, let's try a question. Okay, let's try this one. Consider the following controls in an automobile in motion: the gas pedal, the brake, the steering wheel. What are the controls in this list that cause an acceleration of the car? So first I'll remind you that acceleration is a vector.
B.
Okay, I think I heard a B.
A.
Yes.
Okay, I heard an A. And let me see. Okay, I see Owen says always A, and I see a few more A's from Mehmet, Daniela, and Saja. Yeah, and when you think of the word vector, again, this is the magnitude and direction. So all of these can, let's see, the gas pedal and the brake can very obviously change the magnitude. We know that, right? We can speed up or speed down. Do you want to repeat that, Bafar?
Yeah, the steering wheel also can change the direction, so it's gonna cause difference in acceleration.
Right. So that was the next comment, right? Gas pedal and brake can very obviously change the magnitude. But the steering wheel, although the steering wheel isn't changing the magnitude as much, or I don't know if it can really, I guess indirectly it can. The steering wheel can change the direction of a vector and cause you to move. So if any one of these changes, the vector as a whole will change. So here our answer should be all of them, all 3 controls. Okay, and that's just to get us in the mindset of a vector and a there's 2-dimensional motion here. So let's break down these vectors of position, acceleration, and velocity in terms of two dimensions. So if we know the position vector, of course, of any particle, and we know it over time, we can find the velocity. And so here's the velocity vector, and now the velocity vector is that derivative, or if you remember from chapter 2, we could write this as dx dt if we were in one dimension. Okay, so now we can break up this displacement vector and write it in 2 dimensions. So notice the velocity vector is written in terms of its 2 dimensions, I hat and j hat. And in I hat, we see the derivative of the x position, and in j hat, we see the derivative of the y position. Now this, let me make sure you see the connection here. This notation goes together, right? The derivative of the displacement is the derivative of x and y. Okay, but to make this a little cleaner, you might want to associate this velocity vector with this notation here. They're all equal to each other. It's just a matter of what you're comfortable with working. And sometimes it's a matter of what it is you're given in the problem, right? If you have an equation or if you just have numbers. So the velocity vector.
So is the dy dt the position of y?
That's correct. Dy dt is the position of y, right? This is the position over time. And dx.
And so like, would you have like a y, an equation for y, an equation, and an entire equation for x, and then you'd like put it in there?
You could be given a position and an equation for y and an equation for x, and you put it in there. Yes, you could do that. That is one possibility of what could be given to you. Yeah, and so another way to see it again is that this velocity vector can be written in terms of its x component and y component, and this dy dt is equivalent to this v sub y, right? We could write that out here too. Vy is equal to dy dt. So now we're just writing them different ways, and each way will really give you, a different a different tool set. Like Randy says, if you're given an equation, you might want to use the derivatives. If you're given values, you might want to use the second way. Usually you're given values, usually in this class. Okay, so now that we have this, we can do the same thing we did in chapter 2, where we modeled a particle under a constant acceleration. And we could then write it in terms of these two directions. So we can take our kinematic equations and write every single one of our kinematic equations in terms of their x and y components. And so it'll look like this equation right here that you see. So let's try with our first equation. So you've seen this equation in chapter 2, right? The final velocity in the x direction is equal to the initial velocity in x plus the acceleration in x times time. Well, if we were moving along the y direction, you could also write it in terms of its y components. And both of these here will have their place in an equation. So the full equation that you're used to seeing then is that final velocity. And this final velocity is made up of the x component and is made up of the y component. Both of these make up that vector. And in vector notation, we would write the I hat and the j hat components together. Or if you wanted to write the kinematic equation, you could write the first part of the kinematic equation in x and y, and then the second part of the kinematic equation in x and y. So these are two ways of writing it, but in totality, the vector that you're describing is this. And this is our first kinematic equation that we came up with. Notice again that it's vectors and they're in bold and there are arrows. And so this is the exact equation we saw in chapter 2, and it could be written in its x components or in its y components. How we feeling about?
So like you're saying that they can be, the equation like v of f can be broken into the two different components, and that if we were using like, so then that would like allow us to solve an equation that has motion in multiple directions.
Yeah, that's exactly right. Yeah.
Okay.
I'm going to do one more equation before we actually try a problem. Okay. So let's try writing down one more of the kinematic equations in two components, in its x and y components, and then we'll try a problem that gives us those components. So we can take our big kahuna equation, right? I need another name for that equation, but our big equation, and we can write it again in terms of its x and y coordinates. Here it is in x coordinates, like you saw in chapter 2. And if we were working in the vertical, you would see it here, the way it is written in its y coordinates. So we can rewrite this now for its total displacement, which instead of xf and yf, we could write r. And here it is. So the xf and yf make up the total position, the total final position. And then again, you have two different ways of writing this. You can write everything in terms of its I hat components first, or everything in terms of its j hat components. And if this looks funny to you, I'll write it in shorthand notation really quickly. This would be Rx I hat plus Ry j hat. And so this Rx is equivalent to everything that's in this parentheses in I hat, and then Ry is everything in this parentheses times j hat. You could also write it in terms of parts of the equation. And so this is our first part of the equation. And so here you would have, I'm gonna just show you the next line. So this would be the total initial displacement. This would be the total initial velocity times time. And then here you have the last part, the total acceleration times time squared times 1/2 is right there too. So you can get comfortable writing it either way. I recommend this way because often in problems, you're going to be given separate components, not all the components. So it might be hard to write it in this top way. The other thing I recommend is making a list of everything that you have, and then you could look at each of the equations like this. you could look at each one separately before you bring them together. That's another tip. You write down everything that's given to you, and we're going to practice that right now. And then you can start solving based on what you have in the X and then in the Y. And then at the end, the problem might tell you what's the total. And then we bring everything together like a total, right? Like the sum of the squares. Oh, I'll show you that in a second too. Okay, let's try a problem. Okay, so let's read it first and then we'll break down what are all the components in it. So a particle moves in the XY plane, starting from the origin at t equals 0 with an initial velocity having an X component of 20 meters per second and a Y component of negative 15 meters per second. The particle experiences an acceleration in the X direction given by a sub X equals 4 meters per second squared. Determine the total velocity vector at any later time. So before we pull out everything we know, we can look at some of the options where it says, where it says initial velocity has an X component of positive 20 and Y component is negative 15. So if something is Y negative 15 and X is positive 20, you can imagine counting even like what the shape of the curve will look like based on those values alone, right? So if we plot X and Y, X is going to always move with a positive 20 and Y will move with a negative 15. So we should be in the 1, 2, 3, 4, that bottom quadrant, right? And I hope this kind of, it matches too. Notice that 15 is a lower magnitude than 20. So the curve is growing faster in the X than it is in the Y. I hope that makes sense.
Mm-hmm.
Okay, let's pull out all the information and you guys help me out and we can figure out what is it that we have. So what does everything tell us here now? A particle moves in the XY plane, so we're in 2 dimensions, starting from the origin. Oh, I'm glad the visual helped, Nathan. You want to make these connections and you want to practice drawing this stuff out. So starting from the origin, this tells us that we can say X initial will equal 0 and Y initial will equal 0. Okay, at t equals 0. Okay, so this is our initial time is equal to 0. Any later time will be t final or delta t. With an initial velocity of an X component of 20 meters per second. So we have X initial, we have Y initial, then we have Vx.
Vx initial?
That's right. We have Vx initial is equal to, what is that, 20? And then we have Vy initial.
Yep.
Vy initial is equal to negative 15. Okay, then they tell us the particle experiences an acceleration in the X direction. So A sub X is equal to 4. And what about A sub Y? Anyone? Do we know it?
No.
So the right assumption,
You said A sub Y?
yes.
0.
So I will always tell you to not assume that it's 0, but there's enough information in this problem to tell us that it's 0, right? And Michael, pretty soon that gravity answer will always be right. We'll get there soon. But when you read this problem, and this is totally part of reading the problem, it tells us the particle experiences an acceleration in the X direction. And this is it. That means that the particle is not experiencing acceleration in the Y direction. So it's totally in the wording of this problem. It's like if I tell you the particle is blue, you will write the particle is blue and the particle has no other color because we just said the value. So in this case, we're not actually assuming anything. It's actually in the problem. So A sub Y, I hope, was actually equal to 0 in this case. So we'll take it as that. Okay, so they want us to
So it's gonna be one direction, isn't it?
Can you repeat that?
If the AY is 0, so it should be in one direction, not 2 direction, right?
No, there's still velocity in the y direction. AY means 0, just means that there is still velocity.
And the time 0, there is a velocity. It doesn't make sense.
There is a velocity here. The accelerating in 0 means that the velocity in y is going to remain constant. So when you look at an equation like this, there shouldn't be any time variable attached to the velocity. So what they're asking us here is to determine the total velocity vector at any later time. So total velocity, right, will be total velocity is this. This is how you write the velocity vector. So our goal then is to figure out what is this x component and what is this y component that we're not exactly given yet. Remember that these are initials. So here you either want the final or like the displacement. What is the total? I would say you could use the final here. I think that would be fine. And then it says at any later time. When it says any later time, that means that the equation you're going to solve for is going to have a variable t that can be any time t, and later on you could plug in a time t if you wanted to. Yeah. Okay, so determine the total velocity vector from the information that we're given here. We have this value, we have this value. So we need to find that velocity vector, and let's move this all over to the next slide. Okay, we have our initial in x, our initial in y, acceleration in x, and acceleration in y. My chat is blocking it, but it looks like a 0 to me there. Okay, so again, we want to find that final velocity vector, and for us to be able to do that, we need to get all the components for it here, right? So let's start with our kinematic equations and what we have here. Looking at the list of what we have and what we can plug into our equation, we can just start plugging things in to find this final velocity here. So the numbers that we have just go right in. 20, 4, the time stays as time. The initial y is -15, the acceleration in y is 0, and our constant of time just follows through with the math as time. So our final velocity vector, given from our vector equation that we picked from our kinematic equations, just based on everything that's given to us. Remember, they gave us initial velocities and they gave us acceleration, and they asked us to solve for final velocities. So that's how we determine to use this equation. And we were told at any later time t. So as we bring down the equation, you see that the variable t is left. And we have a vector notation of what's given to us. So this very precisely describes what's happening here, that the x is growing with time t, but the y remains constant over time. That velocity is always going to be a -15, whereas the x component will keep growing over time. Does that make sense? Are we okay there?
Can you repeat the last sentence you said?
Yeah. So what we found here is the final velocity vector. And so the final velocity vector. Oh, I see some thumbs up too. The final velocity vector. And so this vector tells us physically what's happening in the x component and what's happening in the y component. In the y component, you see that there's no constant t, no variable t, which means that v sub y is always going to stay as -15. And so at every point here, you're going to have a -15 growth, but never anything beyond that. -30, -45, and -60. However, in the x component, we see a starting factor of 20, and then we see growth of 4 times t. So at every 1 second, this x component is going to grow. We're going to be here at 1 second. What is this? 20 plus 4, 24. And at 2 seconds, what is this? 2 times 8, 28. And what is this one? 3 times 4, 12, 32. Don't do math in public. But notice how these sections here grow, right? There's always going to be some growth because the time is associated to the x component here. So this gives us a really complete value of a complete look at what is the final velocity vector. Yeah, okay, I see some thumbs up, so we'll move forward. So the final velocity vector, notice we have components and direction. Numbers, I hat, j hat, and the t constant. So at any time t, you can find what is that final velocity. Okay, let's try the second question. Now it says calculate the velocity and the speed of the particle at t equals 5 seconds and the angle the velocity vector makes with the x-axis. I don't know if I remember this part, but let's see what we have. Calculate the velocity at time t and the angle for the velocity that the velocity vector makes with the x-axis. So let's start with our equation and plug in t equals 5 seconds. Right, so this is at t equals 5 seconds. It's very nicely put in there. And so this is where our value t is. So now we have a final velocity vector, for t equals 5 seconds, and we can find the angle based on this x and y component. Anyone? How do we find this angle of this vector? The direction of this vector?
Arctan?
Yeah, we can get the arctangent. Yes, the inverse tangent. Thanks, guys. I see all of you putting it in the chat. Yeah, and so this is where we pull out our vector math, right? We have an x component, we have a y component. We can get theta of that angle, and theta equals the inverse tangent of vyf over vxf, right? And negative 15 over 40 here, and we get negative 21. Okay. Wait, I thought it was x over y. Oh, never mind. Okay, yeah, that's okay. Remind yourself. The final question I think asks for speed, and we didn't go in detail about this, but speed is the magnitude of the velocity. So the magnitude of the velocity here, you guys also know how to do this? The magnitude of a vector? We take the sum of the squares, the square root of the sum of the squares. So the final here, the absolute value, the magnitude of it, the sum of the squares of the x and y component, and you have 43 meters per second. So this vector math, pulling it into our kinematic equations, is very powerful. You can see that we found the final velocity in so many different ways. We found the final velocity vector, right? And I had, this was Vx, I hat plus Vy, J hat. We then found the magnitude of it. We also found it at some time t, right? Vf at some time t equals 5 seconds. And then finally, you found the direction. All of this using vector math, just the x component and y components, and combining it with our kinematic equations. Okay, let's try one more. Determine the x and y coordinates of the particle at any time t and its position vector at this time. Oh, okay. So here's our position vector. And again, you could look through your kinematic equations and find which one you need. Let me remind you that in the first slide, we found all the initial velocity components. We also found the acceleration components. And because we start at the origin, we know that these are 0 and 0 for x and y. So now you can just fill in everything in terms of the components, right? So we have everything in terms of the I hat x components and everything in terms of y j hat components. And we just fill in the values that we know. So 0, because we start at the origin. This initial velocity was given to us. The time t is a constant and it comes down. Ax was given to us. Here's our constant. And the same with j. We start at the origin, so y is equal to 0. Vy is negative 15. And the acceleration in the y direction there wasn't any, so it's 0. And so now if you write this, you can just kind of clean it up a little. And here's your equation then. Your position vector at any time t. So 20t, 1/2 times 4 is 2t squared. And so we see that the position is also going to vary exponentially, while the y position is just going to vary linearly, one component after another. So negative 15 for 1 second, negative 30 for 2 seconds, negative 45 for 3 seconds, and this one is going to change exponentially. So the position vector very nicely matches with our graph. You could write it this way. You could also, if you have another way to get yourself from here to here, that's okay too. There's several ways to solve a problem. Yeah. Okay, our last part of this. What if we wait a very long time and then observe the motion of the particle? How would we describe the motion of the particle for a large value of t? So let's say this were right here, t equals 100. What do we think it might look like? I gotta move my chat box. What do we think it might look like right here? Any ideas, anyone? What do you think the curve would look like at t equals 200?
Will it look almost flat?
Ah, yeah, you guys are, you and Owen are on the same track. Yeah, so this is going to continue that, and it'll start to grow much more in the x than it does in the y. So it'll move faster in the x. And when this curve is flat like this, of course, there's an equation that tells us what's happening, but we also want to be able to describe that, right? So this just means that it's moving closer, it's flatter, it's moving closer to the horizontal position at a much faster rate than it is to the y position. So this has it's not as steep. If it were linear, it would look like this. And it's helpful to always, especially in your advanced classes, like in Physics 102, when we work with circuits and resistance, this will be useful. In some of your engineering classes, my materials class is one of them, this will be useful too. Whenever you want to see what a curve is doing, just draw a straight line and see if it's going, if it's slowing down or speeding up. If you saw a curve like this, you would say, oh, it's growing much more in height, right? Maybe this is a negative value, but I hope you see what I'm saying. Oh yeah, Nathan said it's asymptotic. I don't remember what that means, that it's flattening
So
out.
it's going to approach a number, it's going to look like it's approaching a number, but never reach that number.
That, as soon as you said it's approaching that number, never reach it. Yes, that is, yeah, that's exactly what this curve is doing. And yeah, thanks for.
So it'll look like it's going to get flat, but it actually isn't.
That's exactly right. So this will just continue on forever until we hit the wall of some sort, right? Yeah, it kind of looks like a contour line. It's kind of like a contour line, Luis. But in contour lines, there's an additional dimension, right? Like the closeness of something will tell us about the steepness of it too. Yeah. Yeah, it'll eventually, I should eventually get there. I don't know. I'm not sure, but.
Well, like it goes more parallel. So it never, so between any two time values, you're going to have a slight difference. Like it's going to be slightly lower, but it's never going to be zero. It's never going to be exactly parallel.
Yeah.
So it is still asymptote, however they say it.
Yeah, I don't actually remember the exact definition of asymptotic, but I do know, it sounds very familiar when you say it, Randy, but yes, it becomes more and more and more parallel to the x-axis, but it'll never be exactly parallel to the x-axis. And so we can see that in the equation here, right? It'll never be parallel to this x-axis because you're always going to have some sort of y component here that's going to change with time, right? This whole thing changes and we'll just kind of keep moving there. Okay, so this is, how are we on time? Let's see. Oh, we're pretty good. I got 10 minutes. Let us go into it. I think Yeah, okay. So this is a really good start, and this helps us describe a lot of problems. In physics, our goal is to always model things as simply as possible and to find some common points in problem solving. So when we look at any problem, something being thrown, we can call that a projectile motion problem, and we can make some assumptions here too that'll help us solve these problems easier. So first, let's look at the image before we discuss anything. So here you have the x-axis and the y-axis, and we can call this position for each one. And in general, we know that time is passing, right? So the x position here will change over time, and the y position will change over time. Now you also see position A here, you have a particle, a projectile of any sort that's being thrown with some initial velocity, and here is the initial velocity vector. Now with our experience with vectors, we know we can break this down into its x component, the projection of the velocity vector onto the x-axis, and we could break this vector down into its y component also. And we know that this angle theta is the angle from this x-axis to the actual velocity vector too. So with just this information alone, we know that we can write this out, we can write out relationships here. I'm gonna see if I can remember this, and you guys correct me here if I don't get them right. Is this right? You can start with sine theta. Sine theta is equal to opposite over hypotenuse. The opposite is the y component, and the hypotenuse is the velocity vector, the magnitude of the velocity vector. So if we wanted to find just Vy, which we have here, we could write V, which is the magnitude of the velocity vector, times sine theta. And remember, this magnitude is the hypotenuse, right?
Yep.
And then,
That was a hiccup, sorry.
Oh, and then so for VXI, we could do the same thing. We could write the hypotenuse times cosine theta. So now we have a lot of information just from this vector alone. Okay, so some assumptions we can make. As I throw this up, I hope you all will agree that at some point, it has to start coming back down. And that's because we see and we know that there's this physical force of gravity that's acting on everything. For now, we can say that gravity is acting downward. We'll clean up this definition in a few weeks, but it's acting downward. And so you see this purple arrow, and it is a vector, so it has direction and magnitude. And this is always going to act downward, and it is the acceleration that the particle experiences. So while this velocity vector will have a y component positively up as it's moving up, the minute that it can no longer overcome gravity, that y component is 0 because it no longer can move positively upwards. And now as we start falling back down, gravity is acting down on it. And so we start to see a downward motion. And so we see a downward velocity vector, right? Moving down, moving down. Do we all agree with the movement of the vertical so far? Okay, I see some head nodding. I see some yeses. Thank you, Patricia. Yeah, and Daniela also. Okay, so we all agree with that vertical motion. Now, if we look at the x component, you see that the x component moves, and you see the arrow here tells us the length is the magnitude and the direction is the arrowhead. As it moves from A to B, to then C, to then D, to then E, what happens to this arrow?
It stays the same.
The same.
Yeah, that's right. It completely stays the same. Thank you, Randy and Bafar. It stays the same, and you see that it remains constant. The reason that this remains constant is because we don't see ever any horizontal force that naturally exists at all times that is going to act on a particle. You might quickly say, what about wind? Yeah, wind does happen, and we can account for that in your much more advanced classes very precisely, but that's not always the situation, and it's not a naturally constant. It's not a natural constant that exists. Whereas gravity is a natural force that is always present on Earth and is always pointed downward or towards the center of the mass. But there is no horizontal acting force that is going to prevent you from moving in the horizontal direction. And this is a clue into Newton's laws of motion, the first law, right? If there is no external force acting on you, you will continue moving until something acts on you. Like if you're sliding on ice, which is close to, it's very slippery, no friction. If you keep moving straight, unless something stops you, you're going to keep moving. Of course, in our everyday world, there's wind, something there. Yes, so we are, before I put it in the chat, we are assuming that there is no horizontal force. So we've pretty much come up with these general assumptions, and here they are now in words. So the free fall acceleration, the acceleration will remain constant over a range of motion and will be directed downwards. So in all situations where something is thrown and it falls freely without something acting on it, the y component of the acceleration will always be the value of gravity. And notice here, this y component will always be negative. It's negative 9.8. You could also write it this way. AY is equal, this is an arrow, AY is equal to 9.8 meters per second squared in the j hat direction. But when you write this, when you see this arrow drawn, you are going to see it drawn going downwards. I wanted to go across here. You're always going to see it drawn downwards. Yes, before I put in the chat, the direction is downward. If you just write the component of it and we get the magnitude of AY, this magnitude of AY, and we're just looking at the component, then it will be negative 9.8, where the negative is our way of saying that it's moving downwards. So the value when you're working with an equation, it'll be negative. But when you're looking at vector notation and you're summing up vectors, the vector will just be written as the positive because this j hat will take over the direction of that negative value. We'll clear that up as we go, as we practice it. The second assumption is that you can pretty much say that air resistance is negligible.
So why is I'm confused on why the magnitude ends up being negative if magnitude is positive, because it's the.
Yeah, so when we draw the vector for acceleration, right? This is the acceleration vector, a sub g, and I ask you to write out this vector. You could write a sub y is equal to 9.8 j hat. But when you look at the arrow, that doesn't physically match what's happening. So the magnitude has to be written as negative 9.8.
Oh.
Yeah, so here's where our math and physics needs to match. Now, this is what I'm saying, but I want to show you what it looks like in an equation and show you that the negative will appear, okay? The negative will appear, and we're going to, instead of writing acceleration, we're going to write the g. So I have 2 minutes, and I think we can finish this slide. So all I did was make this picture smaller, and now we're going to look at our kinematic equations in x components and in y components so that later we can bring them together. So velocity in the horizontal direction means that there is no acceleration in the x direction. So anywhere you see acceleration in the kinematic equations, that equation will go to, that component will go to 0. And pretty much what we end up with in the kinematic equations for the x direction is only this one equation. Because if acceleration is 0 in the x direction, that means that velocity, that might be changing in some way, that slope though will always be 0. So every acceleration in the x component will go to 0, and all of our kinematic equations in the x direction will cut down to just this one equation. Okay, now we bring in our second assumption. The acceleration in the vertical will always be a negative g. Again, notice that this is our component form. So now everywhere we see a sub y in the y equations, we can write negative g. And here it is. all of your kinematic equations in the y direction. So this is the x direction, and this is the y direction. So notice that this used to be Vy I plus AT. But now the negative G, when we look at just the value, is interchanged there. And same here, negative G and negative G.
So G is going to be 9.8 and it's negative because there's a negative in there.
It's negative mathematically because there's a negative in there, and physically it's negative because it's pointing downward.
But I mean, when we're putting it into the equation, we're not going to add another negative in, right?
That's absolutely correct. Because we wrote it this way. It's up to you how you want to write these equations, right? I'm more comfortable with writing it this way with the acceleration, and then I'm more comfortable with writing it this way, plus 1/2 AT squared. And then when I write down my list of variables, I write down that A equals negative 9.8. Now, if you want to just skip to this equation, that's totally fine because that's what's presented here. But what is really showing you is that the negative will always be accounted for when you talk about gravity. You either replace negative G with A sub Y, or you write A and then put in the negative 9.8.
So like I usually put in a negative 9.8, but like what equations will we be given? Like what will it look like? Like what's the standard?
This is the standard, this equation.
Okay, that makes sense.
Yeah, this is the standard. And this is, then with that assumption, it becomes this.
Okay.
Yeah, but if you're not comfortable with, you know, where's this negative and keeping the negative, I would stay with this standard and then always write A negative 9.8. Yeah, that's why I do it, because or else I won't be convinced. Okay, I've gone a minute over time, and this is actually exactly where I wanted to stop. So I'm very happy we made it this far. Tomorrow, we're going to see one more class of problems that'll give us another set of equations. And then we're just going to solve a few problems. And see if we have time to get into some circular motion. If we do, great. If we don't, that's okay. We'll continue. I see some comments too in the chat. When we consider vertical movement, going up is positive, downward is negative. Yes, that's correct. Yeah, okay. So I'm going to stop here. And does anyone have any questions before I stop sharing the screen about the lecture so far? Okay. So I'm gonna stick around, and I'm happy to talk about anything anyone wants to talk about. Yeah, I'm gonna stop recording too, if anyone has any last questions. But if not, we're totally done for today.
Thank you, Professor.
Thank you, Kian. Before you go, does anyone here not know how to play Sudoku? That was a real question. Does anyone not know how to play Sudoku?
I'm not good at it.
Oh, okay, that's fair too.
I know the general rules, but I'm not very good.
Okay, so I'll say this then. Oh, okay, some people do not know how to play Sudoku. And yeah, some people have it on your phone. Well, I'm going to release the lab that's for tomorrow, half of the lab, and the first half of the lab is literally a Sudoku game. And it's only because I want you to recognize that as complicated as these variables are and these equations are, there's always going to be a solution. No matter how hard the Sudoku is, there's always a solution. The lab is not due tomorrow, it's always due on Friday. I will show you it tomorrow, but if you want something to release yourself from the exam today, play Sudoku, okay? Okay, I'm gonna stop recording and I'll stick around for any comments, questions. Thanks, guys, and you made it through your exam 1. It's like 4 weeks in a normal semester, so you survived. Bye, guys. I'll see you all. See you tomorrow, 10 a.m. Bye. Bye, everyone. Bye, Robin. Bye, Sanjita, Isla, Owen, Patricia. Bye, guys. Bye, Jonathan. Bye, Bradley. Okay. Bye, Luis.
So you're saying that like in the regular semester, we would be on week 4 right now?
We'd be like midway through, in my class, we would have been midway through week 4.
Wow.
Yeah, not even the beginning of week 4, but midway, like, yeah. That's how much we've covered. So winter session is 5 weeks and we finished 1 week. And so we finished 20%. Bye, Nada. Bye, Andrea. Yeah. Okay, I'm going to officially stop recording.